Hello and welcome to I Know Dino. I'm Garrett.
And I'm Sabrina.
And today in our 346th episode, we have a bunch of news, including a really amazing new Heterodontosaurus, which tells us about how their breathing worked.
And that got you down an Eryctodromius burrow of bird breathing.
Yeah, I had to get the backstory of it, which I'll get into in a minute, but it is very complicated. I also have a very big Eryctodromius burrow for a fun fact, which is about what we eat versus what dinosaurs eat and how it's related. And you have our dinosaur of the day, which is Abidosaurus.
Yep, that one's a sauropod from the Cedar Mountain Formation. Gotta get those sauropods in.
You sure do.
It was a request, too.
I know. But before we get into all of that, we want to thank some of our patrons for helping to keep the podcast running. And this week we have a new patron to thank, and that's Vincentrosaurus. Like Vincent, but with Centrosaurus.
Ooh, good one.
I like it, yeah. And then rounding out our shout-outs, we have Ben at Jurassic Site B, Stefan, Elrex, Mycoraptor, Albertosaurus, JC, John Heck, Ray, and Pipiceratops.
Nice. Thank you so much, everybody, for all your support. That is how we can keep this podcast going from week to week. If you want to get a shout out or some of our other perks, like talking with all the other dinosaur enthusiasts in our Discord, check out our page at patreon.com/iknowdino.
So jumping into the news, I'm going to kick it off with that Heterodontosaurus specimen.
Yeah, how did they breathe?
Very interestingly. But before I explain, I first need to summarize what we know about dinosaur breathing in general. So birds and some non-avian theropods are famous for their air sacs and very efficient breathing.
Mm-hmm.
Their breathing functions in a way that's known as unidirectional. Basically, when they breathe in, they fill their air sacs, and when they breathe out, they empty their air sacs, so their lungs stay full the whole time. It's really awesome. The reason it's called unidirectional flow is because the lungs always fill from the back. So it's not like our lungs where there's only one entry and exit. The entry to the lungs is in the back and the exit is in the front. And they get filled in this really fancy way as a batch of air moves through the lungs. So I'm going to talk through basically how a batch of air moves because it's weird.
So they're always processing air?
Yes. So they're never out of air the way we are.
They never run out of breath.
Exactly. It's really cool. So our breathing is called tidal breathing. So we breathe in and we breathe out just like a tide going in and out. I guess that's the analogy. So when we're breathing out, at the end of it, we're out of air and then we have to breathe in again. Otherwise, we pass out. But birds, when they breathe in and breathe out, they're still getting more air because of this unidirectional flow. But to explain how the air moves through their lungs, I'm just going to follow a single batch of air through the whole system. So you can kind of imagine how the air moves through their air sacs and their lungs. When they inhale, the air goes into the deepest part of their respiratory system, which are the large air sacs in the abdomen. So they breathe in and it goes all the way down into basically the back of the respiratory system. Then on the first exhale, it moves up into the lungs. So the air actually goes into the lungs on an exhale, which is really cool. Then on the second inhale, it moves out of the lungs and into the air sacs close to the trachea. So it's moved from the back bottom of the respiratory system up to the top front. And then finally on the second exhale, it leaves the front air sacs and goes out the trachea. So it actually takes an inhale, an exhale, an inhale, and an exhale in order for that batch of air to make its way through the respiratory system. Yeah. So it takes twice as many breaths in a way to get through the system.
But in the meantime, there's other air going in and out.
Yes. So there's different air going through that circuit in every position. So it's like those workout programs I've heard of where you move to different stations and there's always someone at a station. It's the same way with the air. So there's different air in every position. It's not like it takes 2 full breaths for the animal to get any air into its lung. There's different air coming from air sacs during that time. But really what's generally happening is during the exhale, the air sacs are emptying, and during the inhale, the air sacs are filling. So when they inhale, that back air sac fills from new fresh air, and the front air sac fills from air from the lung.
Hmm.
And then during the exhale, the back air sac fills the lung. So now that back air sac is empty, and that front air sac goes out the trachea. So the air sacs collapse and expand with the inhaling and exhaling, but the lungs always have air in them. It's very fancy, and it always moves in the same direction, too. So it's a unidirectional flow, and it constantly keeps the lungs full of oxygen, basically.
Is that partly how birds can move so fast?
Yeah, it's been proposed that like birds wouldn't be able to fly if they didn't have this fancy unidirectional flow of air, although bats can fly and some other animals can fly. So it might not be entirely a prerequisite, but I think it's still really useful. I'm super jealous of it because sometimes I like running and I feel like I'm always out of breath. And I always imagine like if I was a bird or I had like these extra air sacs and I was like breathing in and out, but I was keeping that fresh air in my lungs, it would be so much better. So if I could ever be a cyborg and change one thing about my body, I think the first thing is going to be bird respiration.
We go from change one thing to the first thing.
Yeah, exactly.
That was quick.
We also think that sauropods and probably pterosaurs had similar air sacs. With sauropods, that's another really good example of why they might have needed that. So you were talking about birds and how like they're moving so much they need it. With sauropods, they have such an extremely long neck that I imagine if they had to breathe in and then breathe out and then breathe in again in order to get more oxygen, that really long time in between how long it took to exhale and inhale down the super long neck, they might start to asphyxiate.
Oh, no.
So presumably, maybe the long necks combined with that inhale-exhale cycle efficiency kept them getting constant fresh air, even though it took such a long time for air to physically move down their neck, which is just so cool.
They had all kinds of efficiencies built in.
They did. Dinosaurs are pretty awesome. But with the exception of theropods, the exact musculoskeletal mechanism for breathing in different dinosaurs is pretty unknown because the soft tissue doesn't preserve, so we can't see all the muscles. We can't see how things squeezed, how things contracted and expanded. I think we talked a little bit about with sea turtles when they can breathe through their cloaca and how like their lungs too, like they have muscles that draw air into their lungs because they can't squeeze the same way since their ribs are on the outside of their body. Lots of animals have different ways of getting oxygen in and out of their body, or even animals that all have similar looking lungs. We have different muscles that bring air in and out of our lungs. So like humans have diaphragms, but dinosaurs did not have diaphragms. They had totally different systems for compressing and expanding.
Poor dinosaurs, and they never got to sing. Oh, I guess they sing in different ways. I was just thinking about how you use your diaphragm to sing.
Oh, yeah. But you can, I mean, anytime you're expelling air, you can sing. So for theropods, the mechanism is a lot like a bellows. They draw air in by changing the shape of their torso, including like a rigid structure. That's why it's sort of like bellows. And then they squeeze all the air out, either by expanding to let air in or contracting to squeeze the air out. The squeezing action is largely accomplished by the gastralia, also known as the belly ribs. Basically, muscles in the front pull the gastralia up and in order to breathe out. It's actually, I think, the same muscles as our abs. It's like analogous to our abdominal muscles that pull their belly ribs in, which I guess is why they're belly ribs, because they're above the abs. But when they constrict their abs, it pulls the gastralia up, and then that pushes the air out of their trachea. But then in order to breathe in, the muscles pull back and down. And the way they do that is the muscles are attached to the pelvis and the tail. So the gastralia sort of get like lifted up and then pulled back down. And that's sort of like the bellows action to push air in and out of the lungs, and probably also some air sacs. Previously, a good set of Ornithischian gastralia hadn't been found, so we weren't sure if they were involved in Ornithischian breathing. And there are some other sources that say no gastralia had ever been found for any Ornithischian.
Oh.
However, there is one other Heterodontosaurus specimen which may have had some gastralia fragments, but they could have been ossified tendons or the smallest ribs, so we're not sure if they were gastralia.
It's too fragmented to know.
Yeah. But obviously that implies that this new Heterodontosaurus does have gastralia, which is pretty awesome. However, up until this point, we weren't sure if gastralia were in Ornithischians at all, because gastralia aren't one of the bones that preserves that well. they're really small and they're also pretty fragile. So you just don't always find them. And it's one of those absence of evidence not being evidence of absence situations, because it's just like something you might not find all the time anyway.
So this study was about a new Heterodontosaurus specimen.
Yes, and it's a really great specimen. And this specific paper is in eLife, written by Victor Radermacher and others. And really, the paper would be an amazing paper and really interesting if it was only about this new Heterodontosaurus specimen, because it is really gorgeous, even without talking about anything about breathing and gastralia and any of that stuff.
Yeah, I'm looking at the images now because it's an open access paper, and it's really pretty.
Yeah, it's really cool looking. It doesn't look amazing without being CT scanned, because a lot of it's still in rock, but they did prepare out the skull so you can see a lot of the details of that without having to scan it, and it does look really great.
There's a lot of good comparison images too, but I guess that goes more to the breathing mechanism part of the paper.
Yes. So this specimen is named AM4766, and AM is after the Albany Museum, which is in South Africa. Like the holotype, AM4766 was found in South Africa, which is why it's in a museum there. It's also where pretty much all Heterodontosaurus specimens are from, although there are a couple named that but not assigned to a specific species elsewhere. It's from the Upper Elliott Formation, which makes it between about 190 and 200 million years old, and at the very beginning of the Jurassic, so it's quite old for a dinosaur. And if you're not familiar, Heterodontosaurus is about the same size as a compy, so it's a little tiny dinosaur.
It's small.
Yeah. This individual does have that gorgeous skull, which includes its crazy front tusk-like teeth, as well as the more normal teeth that are farther back in the jaw, and its beak and the rest of the head. So it's just a really complete skull that looks great. Then there are several other blocks that combine when you stitch them together. I think there's like 5 or 6 blocks total to include much of the rest of the skeleton, which is preserved in an articulated fashion. So it's like you can see while it was alive exactly where all those bones were oriented. And that's why I assume they didn't fully prepare the specimen down to the bones. Instead, they stuck it in a synchrotron X-ray CT scanner to see how the bones were arranged inside the rock. And fortunately for the researchers, it's basically only missing some limb bones and parts of the tail, which means it includes the gastralia, sternal plate, and sternal ribs, which weren't really expected to be found since it's an Ornithischian.
And no gastralia had been found, apparently.
Yeah. And then also all the other details of the skeleton around it, so you can really see where the animal was breathing, other than the muscles, unfortunately. They compare the gastralia to toothpicks.
That's so small.
Yeah, but I think most of them are significantly smaller than toothpicks even. It's more like needles, I would say, and some of them are very short as well. I think there were 9 pairs of them in total, which is, I think, less than some theropods, but still quite a few sets for such a small animal.
Was this an adult? Do they know?
I don't know. I mean, obviously they didn't cut into the bone to do lags or anything.
Right.
But it was around the same size as other Heterodontosaurus, so I assume it was probably roughly fully grown.
I forgot they were so small. Just thinking about gastralia, smaller than toothpicks. It was probably pretty cute in life.
I think it was probably kind of ugly with its weird teeth.
That's true. The tusk-like teeth.
I guess it depends on what covered it. When it opened its mouth, it probably looked freaky, but if its teeth were covered by anything on the outside of its face, that would definitely help. But it does kind of explain why we haven't found these gastralia before when they're so tiny, and if they're in Heterodontosaurus and not a lot of other dinosaurs, then you're not going to find these all that often.
They're probably fragile too, being so small.
Definitely.
Even on a T-Rex, we've seen a few specimens on display where the gastralia is really prominent, and it's a giant T-Rex, and it still looks pretty fragile.
Yeah, and they aren't always recovered even in the larger dinosaurs. But it's not just the gastralia themselves that are really important, because when you combine the gastralia with the sternal plates and sternal ribs, which are fused together, and they describe them as being like tennis racket shaped, they're sort of unusual in the front there, just like how our sternum is on our chest. That's where their sternal plates are as well, so up much closer to the neck. When you combine all of it, you get what's called the quote-unquote full gastral basket.
What?
Yeah, that's what they call it.
Oh, that's just all the pieces.
Yep. And when you combine them, you can get that bellows effect of like squeezing with it.
That's a fun term. Full gastral basket.
Yeah. As a side note, they also found clavicles, which is another rare find for basal ornithischians. So maybe that'll be useful for some other sort of comparison in the future. And then one key thing that they didn't find, which was conspicuously absent, was any sort of pneumatization in its vertebrae, also known as hollow bones or air sacs, because since it's so well preserved, they could look really closely at the details of the vertebrae, and they didn't see any evidence of like air sacs invading the bone. So it's a potential piece of evidence that either there weren't air sacs in Heterodontosaurus, or the air sacs just weren't invading the bones, which is something people have been talking about for a long time. But in the end, they don't think that Heterodontosaurus would breathe the same as theropods, even though they did have gastralia, like theropods have. Instead, they think it was a transition and sort of a combination between the way theropods breathe and what they term, quote-unquote, pelvic bellows.
What?
Yeah. So rather than the gastralia being used to press up on the lungs and or air sacs to form the bellows, they think the hips attached to a novel muscle that formed a bellows basically by like squeezing the back of the lungs and or air sacs. So specifically, the hips have what they call a small anterior pubic process, or APP, but I'm just going to call the app because that's easier to say. So that app that sticks out from the front of the hips is a small spot, at least it's small on Heterodontosaurus, that may have served as an attachment point for a muscle that functioned basically in the same way as the gastralia, squeezing up on the lungs and or air sacs. And there are what appear to be muscle scars on the bone that align in the right direction and things to show that there was a muscle sort of facing where the lungs would have been.
It's a scar?
Yeah, so all bones have muscle attachment points, and then at those muscle attachment points, they leave little, sometimes microscopic, sometimes less microscopic marks where the muscles go into the bone, and you can see those on this bone. Yeah, it's pretty cool.
It is.
Obviously, you can't find it on every fossil.
No, but you can see a lot of details on this one.
Yes. That's part of the beauty of CT scanning, especially when you use a synchrotron. It's high power and you can get the real precision with the micro CT scanning. So on Heterodontosaurus, the app is really small, and so they think it probably functioned in concert with the gastralia. So it's sort of like a half theropod, half app-based squeezing and expansion of the lungs/air sacs. But in later ornithischians, the app is expanded significantly, and we're really confident that they didn't have gastralia, so that larger app may have allowed them to breathe efficiently without the use of gastralia, basically transitioned from gastralia in some common ancestor, and then Heterodontosaurus is sort of that in-between step, and then in later ornithischians, it's got that larger app, which appears to be the main force behind their breathing.
That's interesting.
Yeah. At first, I was expecting, when I saw these articles about like Ornithischian and like that general category, that they were going to be expanding this out to like every stegosaur and ceratopsian and chylosaur and hadrosaur, and that we would just think like, oh, they're missing gastralia, or the gastralia are different than we previously thought. But no, that's not the case. Really, since Heterodontosaurus is one of the oldest known ornithischians, its gastralia probably says a lot more about the common ancestor than it does about later ornithischians. So this is really more about the origin of ornithischian breathing than it is about finding some new gastralia that are relevant anywhere else. Unfortunately, even after all this research, it's unclear if ornithischians had air sacs or not, because this sort of mechanism of squeezing lungs works from the app whether or not there are air sacs there. So it could be that tidal airflow like we have, or it could be the unidirectional airflow like birds have. We still really don't know, unfortunately.
Could it be somewhere in between?
I don't know. I mean, basically, I think you either have air sacs or you don't, but certainly there are some birds or some theropods that have smaller air sacs. So they don't all have massive air sacs like birds do. Some of them have smaller air sacs. So they could still potentially breathe in a unidirectional fashion, but maybe not be getting quite as much fresh air constantly or something. But there is one interesting thing about the app-based breathing mechanism, which is that it may have allowed the wide variety of ornithischian body shapes, which we see in later dinosaurs. So the impressive diversity from ankylosaurs to hadrosaurs and everything in between might be possible because they didn't need gastralia. So like maybe an ankylosaur couldn't have that super rigid body if it needed to use its gastralia to breathe. But if it was using a muscle just inside, sort of like the turtle, then it doesn't have to worry about the gastralia. And, you know, they're more free to have different body shapes because they don't need sort of the outside of their body dictating how they breathe. Because literally, if you're watching an animal with gastralia breathe, it has to squeeze its air in and out in order, you know, like its torso has to like physically change shape like a bellows. But with some of these other dinosaurs, like it's hard to imagine an ankylosaur doing that with such a rigid outer body. Maybe on the bottom, it might be a little more flexible so that it could like go a little concave on the bottom or something. But yeah, I could see how it would really be freeing to them to just be able to use a muscle internally rather than sort of like an overall bony structure for breathing. I just realized I may have misspoken earlier. Birds don't use their gastralia for breathing. They use sort of a muscle, their like hips move to squeeze. So there are some theropods that use gastralia, like non-avian theropods. But I think avian theropods, their lungs are more fixed in place, and then they use muscles sort of in a vaguely similar way to how Heterodontosaurus did.
So for Heterodontosaurus, it would be hard to see it breathing.
Yes. Well, I mean, I don't know.
I guess, yeah, there's no way to know. I can't remember with birds. Usually they fly away when I get near them.
Yeah. I mean, with animals, like if you're inflating your lungs, so the muscle, when it expands, like with us, for example, it's muscle based, but you can still see our lungs expand a little bit. But it's not like our chest doesn't have to like push the air out actively. So if you're breathing shallow, you know, it's harder to see for sure. But I did find out in the course of researching this that there are some lizards, for example, that use the same muscles for running that they use for breathing.
At the same time?
No, they can't. So when they're running, they have to hold their breath.
Oh, is that why they can only run for short spurts?
That might also have to do with being ectothermic. I don't know.
Yeah.
But yeah, so that, I mean, I sometimes think about how like humans, we don't have any of the good adaptations, but at least we can move and breathe at the same time.
Yeah, that seems really bad. It seems like seems like that would put you at a really big disadvantage.
Yeah. So I don't know, they might have an ancestor that had gastralia and then they had to lose the gastralia for some reason or other.
Streamline their body or something.
And then as a result, they had to come up with some other muscles for breathing, and they just used whatever muscles were closest, which are, you know, basically the muscles for moving. And then they got stuck in this really weird situation.
Oh, no.
Yeah, that's terrible. So as much as I would prefer to have bird respiration, at least I don't have that type of respiration.
At least you can run.
Yeah.
For some distance because you can breathe.
Yeah.
Can they walk while breathing?
I don't know how much they walk.
Oh, okay.
I don't know. I just saw it as basically a note about like, this is a weird thing.
That is a weird thing.
Yeah. So it's still kind of unclear about how many dinosaurs had air sacs, but we know now that there are quite a few different mechanisms for how different dinosaurs or ornithodyrans, which is the group that also includes pterosaurs, breathed.
Can you imagine if a dinosaur couldn't breathe while it was running?
Yeah, that'd be ridiculous. I was thinking it makes T-Rex scarier to think about it having air sacs and being able to like continuously breathe.
Right. It's too efficient.
Yeah.
In too many ways.
If it could just keep running the same way a bird can keep flying, it's not great.
In other dinosaur news, in Ashland, Virginia, in the U.S., there's a creek bed with fossils from the Triassic about 225 million years ago. And people who have been exploring the area are hopeful that they might find some dinosaur fossils.
Cool. That'd be nice. We don't get a lot of Triassic fossils in the U.S.
Well, there's no dinosaur fossils that have been found in Virginia yet either, only footprints.
Oh, even better.
Yeah. And a lot of fossils have been found in this creek bed already from a lot of diverse specimens. Fish, plants, reptile teeth, vertebrates, maybe a phytosaur, it's a distant crocodile relative. So what happened is that Michael Stevens, who's an amateur paleontologist, found the site a few years ago. The article that wrote about this creek bed said that he's autistic and incredibly focused and passionate, and those qualities are probably what led him to find this creek bed, which is amazing.
Yeah, that's cool.
Yeah, so he studied the research of paleontologists Robert Weems and Paul Olson and befriended them, and they had surveyed fossil sites around the same area in the 1970s and 80s, and then Michael Stevens figured out that Triassic fossils could be preserved in this particular valley. So he called up the landowners, this was back in 2019, and got their permission to look. And then he started finding fossil fish, so he called up the Virginia Museum of Natural History, and now people regularly go to this dig site.
Nice. That's really cool. That's impressive to figure out, like, preemptively, not stumbling onto a fossil, but just going out there and, like, guessing where you might find a fossil.
Mm-hmm.
That's great.
So I hope they find dinosaur fossils.
I do too. If it's 225 million years ago, then I don't know. Although I wonder, because the Triassic is basically 200 to 250 million years ago. So if you were just going to pick a number for the Triassic, you might say 225 million years ago, just picking right in the middle. So I wonder if they've done the stratigraphy. If it's a new site, they probably, I'm guessing, don't know the exact age of it yet. But depending on where it is in the Triassic makes a big difference on how likely it is to find dinosaurs. Because if it's late Triassic, there was a decent amount of dinosaurs. Still not a lot. There's still a lot of other stuff that was a little more dominant in most ecosystems. But in the early Triassic, you're really not going to find much. And even 225 million years ago is a little bit early for dinosaurs. Hopefully, that'd be really cool. It would definitely be super important if we find more of that mid to early Triassic.
Yeah, but based on how many different types of fossils they found, there's definitely hope.
Yeah. They might also just be able to date it based on like fish and plants and things like that, because some of those evolve a little more quickly than land animals. That'd be great. I'd go for another Triassic dinosaur. They're super weird.
Yeah, or add another state that's found a dinosaur fossil.
Yeah. It'd be on a short list for being the state dinosaur, that's for sure.
Speaking of another state with a short list, Oregon in the U.S., there's a team from the University of Oregon that found a dinosaur vertebra, ornithopod, that scientists think belongs to one of the 2 dinosaur specimens that have been found in Oregon.
Interesting. So they went back to a previous dig site, I guess.
Yeah, there wasn't too much information. The specimen is 103 million years old. The first dinosaur fossil found in Oregon was in 2015, pretty recent, and they're going to be hopefully releasing more information on this find soon. But I thought that was cool. You don't hear too much about fossils from Virginia or Oregon, at least dinosaur ones.
No, you don't. Well, part of the problem is they're covered in a lot of dirt, which makes it harder to find rocks. But I guess in creek beds and things like the one in Virginia, there's a chance.
In South Carolina, Roper Mountain Science Center has a dinosaur-themed traveling exhibit this summer. If anyone's around and wants to go, it's called Be The Dinosaur. And you learn about how dinosaurs survived. It's part of their summer adventure program that's running from now until August 7th. And they also have some outdoor dinosaur trails. There's some dinosaur statues on the trail. I think one of them was a Spinosaurus.
Makes sense. I wonder how out of date it looks. Probably some amount out of date since Spinosaurus changes like every month.
Yes. It does not look like the most recent papers, but it's still cool. In Waynesboro, Virginia, back to Virginia, visitors to the Waynesboro Public Library can now be greeted by a large Triceratops. It's a cast. It's going to be there for a year, maybe longer. It's on loan from the Virginia Museum of Natural History, and they're probably going to be doing some kind of naming campaign soon.
Nice.
That'd be fun. Walk into a library. There's a giant dinosaur.
Maybe they'll have a whole paleontology section surrounding the dinosaur.
That'd be fun. In Calgary, in Canada, Dinny the Brontosaurus at the Calgary Zoo is getting a makeover. And it sounds like it's about time. It's been about 80 years.
Oh, geez.
They've been fundraising the last 2 years. They finally raised $100,000, which is enough to get Dinny structural repairs, new paint, a garden, so that you can take pictures and have family picnics with the dinosaur. And there's going to be a mini dinosaur that kids can climb on.
That's a good idea. We got to get that out of their system so they're not tempted to climb the real one. Or maybe it'll be a problem and it'll like really make them want to climb the big one.
Maybe. So Dinny was the first dinosaur sculpture at the zoo back in 1937. and it was made by John Caverna from Calgary in 1935. It weighs about 110 tons, and it's 107 feet or 33 meters long.
What? 110 tons? That's insane. Is it like solid concrete?
It looks like concrete. It's made in the 30s. I don't know what exactly it's made out of.
110 tons is such a crazy weight.
They need to reinforce the neck and leg. Oh, apparently the repairs are estimated to cost twice as much as they fundraised, but still.
Wow. I'm hoping they must have had to make that in place or something then, because I can't imagine moving a 110-ton sculpture, especially in the 1930s. That is nuts. That's way more than even the real sauropod would have weighed.
This statue was meant to be permanent.
I guess so. I mean, if it lasted 80 years without renovations, it did the job.
Mm-hmm.
They don't build dinosaur sculptures like they used to, apparently.
Well, now we 3D print them.
That's true.
They're much lighter, but easier to repair.
Yeah.
Last, the Science Museum of Minnesota is working on getting Minnesota an official state fossil. Apparently, Minnesota is only one of 7 states without a state fossil.
Interesting.
Yeah.
Maybe they should make it the fossil of the bald eagle, since they have the largest population of bald eagles.
That might have been on their list. I don't remember. The museum's got 8 recommendations.
Although, actually, I'm not even sure if we have fossils of bald eagles. They might not have been around long enough.
Right. It has to be older than 10,000 years.
Oh, probably then. But what are they thinking?
So, no dinosaurs. It has to be a fossil found in Minnesota that's at least 10,000 years old. Some of their recommendations include a bison, a trilobite, a large predator cat, and a shark.
Interesting.
This isn't the first time Minnesota's tried to get a state fossil. There's past bills that have been proposed. There was one for making it a giant beaver in 1988. They've also done it for a trilobite and a bison before.
So the bill has like multiple options. That's really interesting.
It's not a bill yet. It's the museum's recommending, and they're saying, here are 8 ones that we think would be good, but they're also enlisting the help of the public. You can vote on what you think it should be.
Gotcha. Okay, so they're hoping that it'll turn into a bill and then eventually be a official state symbol.
Mm-hmm.
I like the idea of the giant beaver. I wonder why that didn't pass. It's such a weird animal. Like, it just seems fun.
Yeah, I don't know why it didn't happen. I just know it was introduced at one point, 1988. And now into our dinosaur of the day, Abidosaurus, which was a request from PaleoMike716 via our Patreon and Discord. So thanks. Abidosaurus was a Brachiosaurid sauropod that lived in the early Cretaceous in what is now Utah in the U.S., in the Cedar Mountain Formation. It was a sauropod, so it had the small head, the long neck and tail, and the large body that walked on 4 columnar legs. In 2012, Thomas Holtz estimated Abidosaurus to be about 60 feet or 18.3 meters long.
Yeah, it's like average maybe for a sauropod. Seems pretty normal.
Yeah. The holotype, I really wanted to read this name, is Dino 16488.
What's Dino from?
Dinosaur National Monument.
Ah, that's good.
Yeah, it includes a nearly complete skull, lower jaws, and the first 4 neck vertebrae. It was found about 1,200 feet away from the Carnegie Quarry, which dates from the late Jurassic.
It's nice that they found a skull. You don't get that all that often, especially a nearly complete one.
Yeah. Also that you've got these late Jurassic dinosaurs so close to these early Cretaceous dinosaurs.
Oh, weird. I didn't realize when you said early Cretaceous and Dinosaur National Monument, I didn't connect those dots. That is strange.
Mm-hmm. Brigham Young University students and faculty used jackhammers and concrete saws to excavate, and at one point a crew came in and they had to use explosives to blast away some of the rock because it was embedded in such tough sandstone.
Like the good old days, breaking out the dynamite for the paleontology.
Yep. And Garrett, you mentioned that it was nice that they found a skull. They've actually found 4 skulls.
Oh, wow.
That's mostly what's been found are the skulls.
It's such a weird... What kind of a sauropod is all you find skulls? That doesn't... Come on.
So all 4 of these skulls were from juveniles. It's the first time a complete sauropod skull from the Cretaceous has been found in the Western Hemisphere, basically the Americas.
Really?
Mm-hmm. And at the time that Abidosaurus was found, only 8 complete skulls from 120 known species had been found.
Wow, I guess all those titanosaurs in South America, they must only have partial skulls then.
I don't remember when all those were found. They might have been later.
Oh, true. Yeah, like the titanosaur. also known as Patagotitan. I think that one had a complete skull, but yeah, that was found later, I think.
So other fossils were found from 3 other specimens. So in addition to the holotype, they include partial skulls, a partial hip, tail vertebrae, shoulder blade, and some arm and hand bones.
That was decent.
Yeah. It was named in 2010 by Daniel Chur and others. The type species is Abidosaurus macintoschi, and the genus name Abidosaurus means Abydos lizard, and it refers to the town Abydos, the Greek name for the city now known as El Araba el Madfuna, and it was where the head and neck of Osiris, the Egyptian god of life, death, and fertility, was buried overlooking the Nile River, and the name alludes to the fact that the skull and neck was found in a quarry overlooking the Green River. And the species name, macintoschi, is in honor of Jack McIntosh for his contributions to Dinosaur National Monument and the study of sauropods. I'm pretty sure we've talked about him before, but as a refresher, he's a theoretical nuclear physicist professor, and then after he retired, he worked on sauropods. And he's written lots of papers and books on sauropods, and he helped show that Abidosaurus had the wrong head mounted on it in the 1970s. You know, when we figured out that it was the Camarasaurus skull on it.
Nice.
The Abidosaurus skulls were on display at Brigham Young University's Museum of Paleontology, where visitors could see students prepare the bones while everything was being prepared. All 4 skulls were about the same size, at about 1.6 feet or half a meter long.
Yeah, it's not that small. We always talk about how tiny sauropod skulls are, but I guess they're just small relative to the size of their body.
They're small the way T-Rex arms are small.
Yeah, that's true.
And at the time Abidosaurus was named, the postcranial fossils were still being prepared. The 2010 paper that named it said that they would be described at a later date. So I don't know if they're still being prepared. Abidosaurus had a similar skull to Giraffatitan, except the teeth were different. And it had a more narrow snout. It also had small nostrils. Although now most people seem to accept that Abidosaurus was similar to Giraffatitan, in the 2010 paper, the authors wrote that they, quote, considered the decision to recognize the African species as a genus apart from Brachiosaurus to be arbitrary. So they mentioned that Abidosaurus was more like Brachiosaurus instead of calling it Giraffatitan.
Just because they didn't think Giraffatitan was a valid name, so they mentioned Brachiosaurus?
I don't know if they thought that, because they said that they were open to the possibility of Giraffatitan being separate, but said, quote, we do not believe that it is sufficiently justified at present because the identified differences have not been defended as separating genera rather than species, populations, or individuals, end quote. So then there was a post on Sauropod Vertebra Picture of the Week that was published at the time that said, quote, I am sort of nonplussed by this. I'm certainly not saying that my 2009 paper is unassailable. As soon as anyone comes along with evidence that Brachiosaurus and Giraffatitan should, after all, be considered cogeneric, I'll be first in line to hear them out. But I do feel that now 26 osteological differences have been described between the species, the null hypothesis has shifted, and the burden of proof is now on those who wish to synonymize the genera. Quote, we choose to retain the original nomenclature, end quote, is not an argument and doesn't really advance understanding, so I'm afraid I think this was a regrettable misstep, end quote. But the post said they wanted to end on a happy note, and they were excited about the find and happy that John McIntosh got a sauropod named after him.
That reminds me a little bit of like the old school comments about, you know, that are very gentlemanly about like what they think of each other's research.
Abidosaurus was herbivorous. You could probably guess, being a sauropod. It had heterodont teeth, and the upper and lower jaws had 14 teeth on each side. It had narrow teeth, which was unlike earlier brachiosaurids with broader teeth. And the narrow teeth meant that it probably had more teeth than Giraffatitan. It replaced its teeth quickly, even more quickly than Giraffatitan. And Abidosaurus grabbed and swallowed its food. From the paper that named it, they said, quote, the Spartan design of sauropod skulls may be related to their remarkably small size. Sauropod skulls account for only 1/200th of total body volume compared to 1/30th body volume in ornithopod dinosaurs, end quote. So there you go. That's why we think of them as having small heads.
Yeah. It's probably even a larger fraction for like T-Rex.
Yeah. And the others found that sauropods in the Cretaceous evolved to more rapidly replace their teeth, not because of any major change in the diversity of plants around the world, though there were more conifers and angiosperms, but possibly because they changed their diets to eat, quote, highly abrasive vegetation. Or maybe they became more low browsing. They said at the end there was, quote, possibilities to be explored by future work.
That ties in really well to my fun fact.
Oh, good. Well, one last thing. Sauropods probably didn't change much because the long necks and the small skulls helped it to crop food quickly. Basically they're maximizing their intake of food, and they figured it out and they didn't need to change.
Yep. And our fun fact of the day is that some dinosaurs ate grass, but humans eat much more grass than non-avian dinosaurs ever did.
Really?
Yes.
On accident?
Humans eat it on accident, or dinosaurs ate it on accident?
Humans.
Humans definitely eat it on purpose. This is only based on food we eat on purpose.
Okay.
I don't know about dinosaurs.
Right.
I can't speak for them. So not all dinosaurs ate grass. Grass didn't evolve until the Cretaceous, when Abidosaurus was around. But there is an article from 2005 titled Dinosaur Coprolites and the Early Evolution of Grasses and Grazers by Vandana Prasad et al.
Excellent.
I think so. I don't know why I hadn't seen this paper before. I guess we weren't making the podcast in 2005, but it seems like this paper should come up all the time because it's super interesting. So first up, grass is the informal name for the family Poaceae, but I'm just going to call them grasses because that's a lot easier to say. Humans mostly eat the fruit of grasses.
Okay, that makes more sense to me.
Yeah, basically everything we eat is fruit. So like that food pyramid that's like eat a bunch of fruit. It's like all the grains we eat is the fruit of grasses, basically. But anyway, that's a whole nutrition versus scientific nomenclature thing that I don't want to get into. So back to dinosaurs. Herbivores like cows and presumably some dinosaurs, like maybe Abidosaurus, can chew and digest leaves of grasses as well, not just the fruit.
Whenever I think of grass, I'm only thinking of the leaves.
Yes. Yeah, like
That's why I was
like
confused.
A lawn, for example.
Yeah. I was like, humans eat lawns? I don't think so.
Yeah, grasses are a really diverse group of plants, and they're fascinating and super important in all sorts of different ways. But grasses, like many plants, contain phytoliths, which sort of like gastrolith being a stomach stone, a phytolith translates as a plant stone. They're hard silica structures that serve a variety of purposes in plants. Sometimes they form a structure like a skeleton. So if you raise a plant in certain plants in soils that don't have enough silica, they won't be able to stand up. They'll be all floppy because they can't like build their skeleton, basically.
They need their nutrients too.
Yes. And these phytoliths can also serve as nutrient storage. Sometimes other things can be kept among the phytoliths to be extracted later. Like I think calcium or something can sometimes be stored in the phytoliths, kind of like osteoderms, I guess, in dinosaurs. And then they also might be used to protect themselves from hungry animals like humans, because we can't chew on grass. It would destroy our teeth because the silica is very hard. We don't have continuously growing teeth, and we only get our one set as adults.
Yeah, as adults, one set.
Yeah, so we can't chew on grass. The biggest problem there is that it would wear down our teeth and you'd be in trouble. But other animals have adaptations to deal with that. We don't know for sure that that's why, one of the reasons why they have phytoliths, but it could be. So the important thing in that paper is that researchers found those hard silica phytoliths in several coprolites. And under a microscope, the phytoliths have very unique shapes, just in general. Phytoliths have really unique shapes. It looks sort of like when you're looking at viruses or bacteria or any other microscopic thing under a microscope. You can see all of these little details, and the shapes are all crazy, and they're very unique. And with the phytoliths, you can actually identify the group of plant that the phytolith originally came from just by looking at it under a microscope in some cases. And that's really helpful because phytoliths usually outlive the plant itself by thousands of years.
What?
Yeah, so since they're a really hard silica structure, and silica is pretty unreactive and pretty tough, phytoliths from grasses and other plants often remain in soil for thousands of years after the plant is long since decomposed. The rest of it's decomposed. And in the case of a coprolite, we know that that's a great place to preserve something. So if a dinosaur, for example, eats a plant and these phytoliths end up in their coprolite and then it gets all sealed up and fossilized together, there's a chance that you can get in there and find the phytoliths.
Get into those coprolites.
Yeah, it's amazing. But like tens of millions of years later, sometimes these phytoliths have still preserved in the coprolite. In this case, we were able to identify that some of those 8 groups were from plants. So in this case, they had several coprolites. All of them are believed to be from titanosaurs, and the coprolite had more phytoliths from other plant groups than grasses, so grasses may have been just a small part of their diet, which is why I say dinosaurs basically didn't eat that many grasses, although they did eat some grasses because we found them in their poop. It's only one way for them to get there. Well, I guess there's more ways, but there's one likely way for them to get there.
The most likely way.
Yeah. The other things that were more common, in aggregate at least, are conifers, cycads, fungus, and algae were all also in the coprolite, and phytoliths from those things in some cases. Those coprolites were from the Maastrichtian of central India, so this is at the very latest end of the Cretaceous, so it's not too surprising that they were eating grasses because we knew that grasses evolved sometime during the Cretaceous.
But they chose to eat these other things.
What do you think would be the tastiest of those options?
As a human, so I'm biased, the grasses.
But this is just the leaves of the grasses, because that's where the phytoliths are.
Oh, you're right. Okay. Never mind. The fungus.
Yeah, that's what I thought you'd go for, because mushrooms are tasty.
Mm-hmm.
So at the time of that research in 2005, prior to their publication, we had estimated the likely evolutionary origin of grasses as about 80 million years ago, which puts it like in the middle of the late Cretaceous, and that would mean that some of the dinosaurs encountered the grasses, but really not all that many in aggregate, since dinosaurs were around for like 150 million years, and they were only around for like 20 million years after that 80 million year mark. But after this, in 2018, in National Science Review, Yan Wu et al. Described, quote, a complex mineralized bacterial biofilm on the teeth of a hadrosaur.
That's what happens when you don't brush your teeth.
Yeah, it's great. So they had like a fossilized, crazy bacteria biofilm on their teeth. And when they analyzed it, they found that it had phytoliths that appeared to be from a grass on it.
Oh, it was a grass eater.
Yes. They were essentially finding bits of grass stuck in their teeth about 101 to 113 million years later, since it's from the Albion.
That sounds unpleasant. You got the stuff stuck in your teeth. It's created a film over your teeth.
Well, this is like bacteria on the outside of the teeth, and they might have even formed after the animal died, because after all, it is a fossil. And it's really tiny stuff. I mean, we have all sorts of microscopic stuff in our mouth. But the interesting piece here is that since it was from an Albion deposit, roughly 100 to 110 million years ago, that means that technically we have evidence of grasses from the early Cretaceous now, not just the late Cretaceous. And in that paper, they thought that based on the type of phytoliths that they hadn't branched off from another group, and that might push the origin of grasses back to 120 to 125 million years ago, and now we're getting more dinosaurs that might have encountered grasses. But even still, by the late Cretaceous, it wasn't a huge part of their diet. We know that even if there were grasses around then, they weren't like the dominant plant in the ecosystem, because we have all sorts of pollen spores, and we have these phytoliths and all sorts of things that we can work from to figure out what the common elements of the ecosystem were. Unfortunately, we don't know how much of that hadrosaur's diet was grass, since it's just that bit on the tooth. We don't have a coprolite to work from. Coprolites and gut contents are what you really want when you're trying to figure out what animals ate.
Oh, yeah. I like those studies.
Yeah. So now I need to justify my statement that humans eat more grass than dinosaurs, because we know, at least in the case of those titanosaurs, less than half of their diet was grasses. But humans skew herbivorous in our diets, specifically relying heavily on grasses for most of our food, actually. So more than half of our food is grass. Some of the grasses people eat are bamboo, barley, maize, also known as corn, millet, oats, rye, rice, sorghum, sugarcane, and wheat.
I'm hungry now.
Those are all types of grass. A lot of people don't realize bamboo is a grass because it's huge, so people think it's a tree, but it's a grass.
So pandas are also grass eaters.
Yes, they are, yeah. According to the Smithsonian, about 4 million years ago, our ancestors ate 90% fruit, but by 1.4 million years ago, grasses accounted for 55% of human diets.
I wonder why. We get more nutrients from grasses than fruit, maybe?
So they think, well, back then humans were mostly in Africa, maybe exclusively in Africa, and the forests in Africa had turned into savannas. And there's a lot of details here, but basically that analysis was looking at the ratio of C4 to C3 plants. The C4 carbon fixation photosynthesis pathway is evolutionarily pretty new. Only about 3% of plant species use the C4 pathway, but most C4 plants are grasses. So usually when you're doing the C4, C3 analysis, what you're really trying to do is figure out how much of the diet is grass. So in that time period, most of the hominid diet came from C4 plants. It probably means that humans were eating lots of grasses. Interestingly, according to the UN, cereal grains account for about half of humans' dietary energy supply, which is pretty similar to 1.4 million years ago, which is also known as the Paleolithic.
So our diets haven't changed that much.
Yes, eating mostly grains is a paleo diet. Despite what everybody wants to believe, I guess.
Not everybody.
A lot of people. Something about the paleo diet just really rubs me the wrong way.
It's probably because it's got paleo in the name and you think, that's not dinosaurs.
I think it's because it sounds scientific and it's so pseudoscientific because it's based on like a very specific group of humans that were living in a place where plants weren't growing. Anyway, it bugs me.
But also the lack of dinosaurs.
I guess, yeah. So the fact that we eat a lot of plants means that we are more herbivorous than we are carnivorous, that most of our diet comes from plants. But I think when people think of herbivorous, what they're really thinking of is folivorous. At least that's what I personally am thinking of. Folivorous or folivore is the term for an animal that eats leaves. Like you were saying, when you're talking about grass and eating it, you're thinking of the leaves. You're not thinking of the fruit that comes out of the plant. So even though humans can be herbivorous, we can't really be folivorous because leaves typically have those phytoliths in their leaves and it would just wear down our teeth too much. I guess there are some exceptions because we eat salads. Those must not have a lot of phytoliths. Otherwise, every person that ate a lot of salads would be wearing down their teeth.
Trouble with their teeth, yeah.
Yeah. There is one reason that I probably shouldn't be too hard on the paleo diet, and that's because we have modified our cereal grains a little bit. And so nowadays they do lack a few nutrients, which they may have had in the past. Human cultures have typically mixed with legumes in order to balance out what's missing from cereal grains. You can't survive on just cereal grains. And I found this list that I thought was just kind of funny. So they have a grain mixed with a legume. So there's lentils with rice, corn with beans, tofu with rice, and then the American example is peanut butter and wheat. Which that was funny because all the other examples are things that kids and adults eat, and then our example is like adults don't eat that.
Speak for yourself. I love peanut butter on toast.
I don't eat enough peanut butter.
I eat all the things you just listed.
I feel like my diet skews way too hard to the grains and not enough to the legumes, and that might be why like the paleo diet and simple explanations like that are useful to get people a little bit away from just like 90% grains. So most of the snack foods at least are grains in the US. But I also think it's fun to think about how dinosaurs would have balanced their diets, because we know that some hadrosaurs ate wood to get at shelled creatures, possibly for the calcium or maybe for protein or some other nutrient that was in these animals. And chickens also have pretty similar diets to us. They balance fruits, vegetables, grains, and occasionally meat.
Really? I didn't know about the meat.
Yeah, because they'll eat each other or they'll eat eggs and things like that on occasion. Chickens can also eat grass, which I was a little surprised when I read that. And then I remembered my friend who cares about his lawn and also cares about his chickens and noticed that they were eating his grass and had to figure out how to balance these priorities.
Yep.
So, yeah, there are modern dinosaurs that eat birds. That's why I had to say we eat more grass than any non-avian dinosaur did, because there are animals like geese that eat tons of grass, and there's no way people could keep up with that. So if you're ever looking for a cocktail party fact about dinosaurs, tell people that we eat more grass than dinosaurs did.
I don't know if that would be my go-to dinosaur fact, but yeah, that's an option.
This is episode 346, so that would be roughly 346th on the list of go-to facts.
Got it.
I'd say.
And that wraps up this episode of I Know Dino. If you want even more dinosaurs, then check out our book, 50 Dinosaur Tales. We wrote some short stories about the more recently discovered dinosaurs and imagined what their life would have been like. There's a couple of, maybe I can call them Easter eggs in there, where you can see how the stories are linked together. So if you want to pick up your copy, go to bit.ly/50 Dinosaur Tales, and that's 50, and then Dinosaur Tales, TALES, because we're telling stories here. And if you like what you read, please leave us a review. Thanks again, and until next time.
Good day.